Okay, we have an infinite series, and we want to find out if it converges or diverges. So with this one, what comes to mind is to use the integral test. We can use the integral test on this one for three reasons. It is continuous, it is positive, and it is decreasing. It is continuous because the only thing that we can plug in here that would make this, that would yield a hole in the function would be if we plugged in -1/2 for n. But this is a series, so you can't really plug in -1/2. We're going from 1 to infinity, so -1/2 wouldn't make a difference. It is continuous as a series, as a sequence in a series. And it's positive because we can just tell. We don't really have to prove, again, that it's positive because it's already obviously positive. There's no thing that's negative that you're multiplying in there, so this is going to be positive. The one that we do have to show is that it's decreased. So the way we show that is by two ways. You could either take the derivative. If the derivative is negative, it's decreasing. You could also plug in n+1 for each n and find if that's less than just this. So we have 2n+1, and we want to have this be greater than when we plug in 1/2n+1 plus 1. Because this is the next term in the sequence. So if you have a sequence, you have a sub n, and then you have a sub n plus 1, and then you have a sub n plus 2, and so on, right? So that's what this is. We want to make sure that the next term is smaller than the previous term. Got that? So this would be 1/2n plus 3. And this is less than 1/2n plus 1, obviously. But your professor lacks common sense, so you would have to cross multiply. 2n plus 1 is less than 2n plus 3. And now we have these cancel out, and 1 is obviously less than 3. You really, if your professor doesn't see that at that point, there's no hope. There's nothing you can do. So yeah, you have to cross multiply and bring it down to the end, even though we know at that point, because this denominator is obviously going to be bigger, this is going to be smaller, but you have to go all the way down. So that proves that this is decreasing. So it's met our three conditions, therefore we can use the integral test. What does the integral test say? Well, with the integral test, you take the integral of a function f of x, which has the same formula. So you would take the same formula like this. And you would go from 1 to infinity. And if this converges, this also converges. If this diverges, this also diverges. So that's how that works. It's pretty simple. So now we can take the limit as t approaches infinity, because remember, we've got infinity there. We need to replace that with a t, 1/2x plus 1 dx. This one's pretty easy, right? You would just take the natural log of the absolute value of what's in the denominator and divide by 2. So we would get 1/2 natural log of the absolute value of 2x plus 1 as our found integral. And we have bounds on this. We have bounds from 1 to t, with the limit as t approaches infinity. So when we have bounds, we subtract the bottom bound from the upper bound. So the upper bound would be 1/2 natural log of the absolute value of 2t plus 1. The bottom bound would be 1/2 natural log of 3. The absolute value goes away because it's just 3, so natural log of 3. And we're taking the limit as t approaches infinity still. So what would happen with this, if we plug infinity into that, the natural log goes to infinity. So infinity times 1/2 is still infinity. This is infinity. And you subtract some weak number from infinity. Infinity will take it still infinity. So infinity. That means that our integral diverged, and because our integral fulfilled, because this fulfilled all of these conditions, then this also diverged.